Sorry about that. Okay, I think we've got enough to get started now. And if anyone wants to join, they can. This is the final presentation. So what we're going to do is talk about, I'm going to cover an overview of the project. We're going to look at the vehicle data EDA, and we'll take a look at the accident EDA, the modeling aspect, and then the solution dashboard. Yep, it's recording. Yep, it's recording. And after we've taken a look at the solution dashboard, we're going to basically allow people to talk about, what they found good about the project, what they've learned, any difficulties they encountered, and any future steps they're going to take, in terms of learning and whatnot. And, if there's any sort of, and I'll also as well reiterate that because we've worked together for the past couple of weeks quite closely, we've got to know each other and things like that. Make sure you get everyone on LinkedIn, endorse everyone that you've worked with, leave recommendations for everyone that you've worked with, and that just helps with bolstering your reputation on LinkedIn, and it can make it, it builds your network as well. And, especially in today's climate, networking to find jobs in data related fields is very valuable. But we'll get to that. Yeah, I've got a list of everyone. Yeah. Don't worry about that. So let me just share my screen, and I will give basically a rundown of the project and how we put it together. Unfortunately, I haven't got two screens at the moment. I'm waiting for it to be delivered, but so I can't see any questions or anything like that at the moment. So the initial task was to predict road traffic collision severity, and the data that we used was from the Department of Transport, and it was two data sets. One was a vehicle data set, and it entailed all the vehicles involved in particular instances, particular accidents, while the accident data give you the sort of circumstances the accidents occurred in under. And these two data sets could be linked by the primary key, which was the accident index. Now, looking at the data before the task was actually launched, before the project launch, I had a look at the data very, very briefly, and thought, there's a couple of different features that we could explore, not just the prediction severity part, and that was geospatial heat mapping, time series analysis, and any predictions, and also obviously the vehicle analysis and possibly a prediction, but that didn't turn out to be very fruitful. But the vehicle analysis was very, very strong, and it did give us a lot of insights. So as we had 4 different routes, I thought, to try and reflect what it would be like working in industry using this kind of data for a client. And the first instance of any project is the data engineering side. The data engineers are the ones who basically maintain the infrastructure for the clients, basically the data infrastructure for the clients, and they would be the ones ultimately producing the data, pulling it together, and to sort of make sure that there is pipelines of data that data scientists can use to analyze and make predictions. So in that case, we nominated data engineers, which were OAS and J, and they were led by Vivek, and they put together 4 different data sets for each pipeline. And the pipelines were obviously predict severity, geospatial time series, and vehicle analysis. And then each one of these pipelines had their task leads and their co-leads for every for every individual task under that pipeline. So your data pre-processing, your EDA, and your modeling, if that was required. And the people within our task group that were not the leads or the co-leads, what they basically were sort of encouraged to do was to work on any group that interests them, and even to, you know, jump from one pipeline to the next and just learn, and that give them the opportunity to learn as much as possible, because each sort of pipeline would take a different direction depending on the insights that were found, and depending on the tactics that were used and applied to the data set. And then the plan was at the very end, for the model deployment and the model development and the deployment, it was going to be solutionized. And we first thought, you know, we could use Flask, we could use Streamlit, and we've gone with Streamlit to create a solutions dashboard, which includes the insights that were gathered from each of the pipeline teams. And of course, you know, the plan was to deploy a live model that was able to have a batch inference. Unfortunately, that wasn't possible, as we found out through the modeling stages. The data just wasn't quite good enough to give us meaningful results. And you know, Michael and Oasis and everyone else who tried to do some of the modeling through the absolute machine learning book at the problem, tried numerous techniques, oversampling, undersampling, smoked, and, you know, a number of different class balance techniques. And it just, you know, it seemed to work quite well, but then when it actually come to predicting on data, it didn't see, it fell flat. And we sort of guessed that it was due to the fine line between fatal and serious accidents. Also, the data itself, you know, there wasn't any sort of significant importance when it was measured in, you know, for each particular model that everyone used. So like random forests and whatnot, couldn't really find anything really that stuck out, which told the story, told the story towards the outcome being severe or fatal. And it turned out like the model, you know, most of the outcomes are slight accidents, and the model was basically just, even if it, you know, it was guessing 85% of the time it was slight, it's going to be right anyway, because, you know, 85% of the data in the, you know, was slight accidents. So we sort of come to the conclusion that to if we were going to take this further, and, you know, try and produce a model that actually could be put into production, we would have to go back to the original client data, and we would have to sit down with the data engineers and basically come up with a plan to get the most out of the data that was kept on the client system. Now, that is what would happen in real life. And Michael, he's going to run through the modeling processes and, you know, and just show you concretely the issues that we faced during this time. Overall, the project went quite smoothly. There was a mass amount of collaboration. I'm in a couple of different projects on Omdena, and, you know, a lot of them don't even have half of the collaboration that we've had, and, you know, the active participants. You know, we've got a good number of active participants who've all tried, you know, doing their own analysis, and, you know, learning from other people, applying it themselves, and producing notebooks. I think we've got notebooks coming out of our ears, all with valuable insights, all with valuable techniques. And of course, that's allowed everyone to learn a lot more, and very quickly as well. And I'm sure we'll hear some of the stories about that later on when we come to the end of the presentation. So let's crack on, and let's go from the start. Basically, we're going to have an overview of the vehicle analysis data, an EDA exploratory data analysis of the vehicle data, and that's going to be led by Shrawan. So if you would like to share your screen and load up your presentation, that would be fantastic.
Yeah,
and I'll go off camera and mute.
Thank you, Rich. Am I audible?
Yes, you are. Yeah.
Is my screen visible?
Yep, all visible.
Okay. So yeah, thank you so much, Rich, for giving this opportunity to work with a global team. And thank you so much to everyone who collaborated in this project. So let me start with the vehicle analysis and prediction pipeline. So yeah, so first of all, applying a machine learning approach to any data, what we should do is know the business problem. So the main business problem, was to understand how accidents were more likely happening in the road, and what were the main reasons that cause road accidents, and what could we do to like uh, decrease the amount of collisions, like road traffic collisions. So after framing the main business problem, we set out to frame the machine learning problem, and to see first the objective was to identify the machine learning, state the machine learning problem for it, and extract data, and then go through the data description and perform some EDA on that, and then finally conclude from those analysis. So yeah, the main machine learning objectives that had been set in this pipeline were to do the in-depth analysis of vehicles involved in collisions, and try to create a model, if it's possible, to create a model to predict the likelihood of specific cohorts being involved in a collision. And the next in the in the data science pipeline, so what we do is like extract the data. So it was easy for us since the data came from the open data website of the UK government, that was published by the Department of Transport. And then yeah, we had for this pipeline, we used the vehicle data, which consisted about 2.1 million records with 39 features. So every instance of records in the data file represented the involvement of unique vehicle in a unique traffic accident. So it features various vehicle and passenger related properties and features as columns. And then yeah, after going through each feature and an understanding about them, we could categorize it into them into four specific categories, such as some are related to accident specific, and some related to vehicle specific features, and some of the features were more specific to the regions of accident, and finally some features were more specific to driver driving the vehicle. um, and then what we did was just for just going through the data, we saw that yeah, the number of collisions, road traffic collisions, had significantly raised after 2008. Yeah, and then slightly and then decreased after 2015. So we could see like 50% of the accidents were a number of accidents recorded were below 2011, and 75% of the accidents recorded were below 2014. So we could see a significant decrease though. And going through the age of vehicles. So the age actually signified the age of vehicle from the after the manufacturing time. So some of the interesting thing that we could see was that most of the collisions that were recorded in and put in the data set recorded 7 years aged vehicles, so they were more likely to be in an accident than the vehicles that were older. And from the data itself, we could see that the data was a lot of it was so skewed, and we could see that about 22% of the whole data if we could compare, we could see that 22% of the data comprise of vehicles aged 7 years old. So this could be some of the things we could consider here is like older vehicles were like more or less likely to be in collision either due to uh, I, we could consider a number of factors could be considered here, and one of them could be like most of the vehicles, like old age vehicles, were not driven in the road itself, or could be the reason, might be the reason. But the interesting thing is that like newly bought vehicles or the vehicles itself, like they make up a lot of they make up a lot of data in the whole data set, right? Count in the whole data set. And then, after going through the missing through the data, we could see a lot of missing values in the data sets itself. So only some of the features, such as junction location, junction, like journey propose of driver, some of only some of the features had at least most of the instances were filled with the feature were filled for each of the most of the instances, but we could see like some of the features are the values has been missing simultaneously, such as make, model, or propulsion code that were more specific for the engine itself. So when the engine, it seemed like when the engine itself, so most of the data related to engine, all of the features such as make, model have been missed out at the same time. So a lot of inconsistencies here, and then yeah, we try to see the distribution of the feature itself and try to impute and see how we could do better on analysis. And after applying mode, mean, and median imputations for engine capacity, since the engine capacity was highly skewed, and we try to see apply some imputations on that, and we could see that mean imputation performed only there was only a minor change in the distribution after imputation, which could further help us for analysis on this. Um, yeah, and then we try to go over the feature driver IMDT style. Clearly, we could see that none of the imputation method worked, and since we didn't have any target feature, we could not make any use of it. And since 30% of the data was only available for driver IMB design, so no, we could not gather any insights from it. It could be useful. The feature driver IMB design could be have been useful, but since the data itself had only 30% of it, so we cannot use it for any analysis. We cannot inference any insights from it. And then one interesting thing that we could see from the data was like a single accident had involved about 53 vehicles in in an accident, in a single unique accident. So uh, this might be any erroneous data recorded in the database, or might be any disaster that involve a lot of vehicles. Uh, but the overall thing that we can see is like the on most of the sorry and yeah, so some other exploratory data analysis we could do was on the distribution of accidents across vehicle type. So if you go through the graph, the figure itself, we could see that nearly 70% of accidents are car accidents. So it raised another question that so what may be the reason that what makes car accidents more prevalent, or is it due to cars population in whole Liverpool was it might be larger than any other vehicle. So that might be another reason for it, but it poses a serious question that what since car have a large amount of accidents recorded, so there must be any like reason for such incident happening with cars. And yeah, we could see that that males are twice more involved in collisions than females. This could be, also this could be due to we have to look for this for concluding anything from this. We must also try to gather insight from what is the proportion of female and male drivers in the place itself. So before making any conclusions like male are more likely, we must consider the proportion of the drivers in the place. And yeah, though, but since it also shows that males are more likely, more twice likely than females to be involved in accidents. So yeah, the next is distribution of home area driver. So yeah, it is obvious that a lot of accidents happen in urban areas and quite in small towns. Mm, yeah, and some interesting thing we also tried was to see if we can find any insights given gender and engine capacity. And yeah, we assumed if females were riding heavy vehicles, and if females riding heavy vehicles were more likely to be involved in collisions, but it was not true. Since we could see that most of the accidents were caused by females were driving by less powerful vehicles, and whereas the ones caused by males were due to powerful vehicles. So we could see that a lot of accidents happen while using the large engine capacity vehicles, right? And, and then yeah, some of the interesting thing about the driver itself. So we could see that drivers aged 26 to 35, and yeah, yeah, taking from the range from 26 to 45. If you take both, then they make a lot of uh, they are more frequent in the whole database. So we could see that we have some records from a record of some aged from 0 to 52 and some over 75. And yeah, we could see that young 26 to 45 age people were more involved in collisions. And yeah, about going through the distribution of age group, it was interesting to see that as I've said earlier, that kids aged from 0 to 5 were driving vehicles, but it can't be true. But which may be enormous. But apart from that, we can say that people aged 55 to 65 drove vehicles with most engine displacement on average. If we go by the distribution, the date, the model or make, the make, we could see that Vauxhall, Ford, and Volkswagen, Renault, they themselves make about 40% of accidents. So this might help us to get some insight, but still, uh, for this to get any further insight, further conclusions, we think that we need to first understand the proportion of vehicles in for that place, and before making any conclusions like these types of vehicles are more likely to be in accidents. Mm, yeah, it seems obvious since petrol vehicles are more prevalent. Um, and yeah, we could see that most of the accidents were happening while the vehicles were going ahead together. And yeah, and interestingly, we could see that overtaking near side had recorded data very comparatively very less recorded, like. And so if we had gone through the distribution of accidents across junction. So if we see, so most of the accidents are not at or within 20 meters of junction, but if we combine the first three, we could set out a parameter around the junction and see that junction near the junction near junction or the like mid junction are more are the areas where a lot of collisions happens. And since accidents happen, while it's more likely that accident happen when two vehicles collide than the vehicle only single vehicle getting in an accident after going through the data set. So it's obvious that a lot like front part of the vehicle, or this might not get us more insights, but yeah, it's obvious that one of the vehicles front side could be have been affected by the accident. And if we see the distribution of accident across gender and commute, while most of the accidents caused by males were due to work-related commute, and accident caused by females seemed that they were due to their commute to drop or pick up their children from school. Mm, and then so yeah, this analysis might not pose any inference, get might not get us more inference, but still we could see that a lot of the regions for commute were not recorded, right? And then yeah, accidents happen when people were traveling as a for the purpose of a part of a work or commuting to and for from work. To conclude any insights from it, we could even compare with the time. If we have a time feature, we could see at what time the accidents are more prevalent, or to conclude anything like commuting to or from work at this time is more prevalent, right? We could set out, we could inference something like this is the peak hour that more accidents could happen. So we could combine this with the time related features of any analysis. But still, um, so yeah, uh, since the whole data science project is very iterative, uh, the data science project never ends. It just we end it, but it never ends. So we could not we could not go with the second objective. So why model could not be developed, right? So the given data set comprised of only vehicle passenger related information which were involved in accident. That implied that we do not have entries apart from vehicle involved in accident. We have a pure data set. And the second thing was like we were trying to solve seemed like a novelty problem. So exploring data to gather information regarding their importance has to be performed without a target variable. And yeah, and the second thing that that hindered the model development was like we have to validate the model itself. So though trying to solve it as a novelty problem, we would require a data set of vehicles and the characteristics which make them less likely to win collision. So we could validate in the real world. Thank you.
Thank you very much. That was excellent. And it is, you know, the insights that you've been able to provide very much match British insurance companies. The age group, 26 to 35, I think it was. when you you get a car and you pass your test in the UK and you apply for insurance, the the cost involved for insuring someone who's 26 to 35 is massive compared to the following age group. And also when you applying for British vehicle insurance, they ask you, what are you going to use your car for? And if you put things like for commuting, business and whatnot, your insurance goes up again. So it's obvious that they've looked at this data and made the same insights that we have, where a lot of the report, ones that we have reports for in terms of collisions have been, journeys for business and in that particular age group. So it seems that, they are the most at risk, and that's certainly the way the insurance companies see that. So very valuable insights, and already we can see that it, based on other sources of data like insurance companies, that our insights are valid, and this is, it's being observed in real life, and it is affecting insurance policies and whatnot. So we've nailed it. You've nailed it with that vehicle analysis. Very well presented. Thank you very much. Yeah, we've got 2 minutes left. So just quickly, has anyone got any questions about that analysis or any comments at all? If not, I'll just restart the meeting. Cool. Okay, what I'll do, I'll end the meeting, just refresh and rejoin, and Kevin will take us through the EDA for the accident data set. Okay. Is everyone, Kevin, let me just allow you to share your screen. If you would like to share your screen and go ahead, that'd be great. I'll turn my camera off and mute.
Okay, so everybody can hear me and see that?
Yep.
Cool. So I myself and Ibrahim was the task lead, and I was the co-lead on the accident EDA on the predicting the accident severity. So what I've done, I've just put together a quick slideshow, really, just to show some of the highlights and just some of the things that we did during that process. So as we can see from the start there, we only had a data set from 2005 to 2010, which was great. And the reason for that was in the hope that if we got this to work, we could use that as to train the model and then use the future data to see if our predictions were correct. So we had 1 million lines of data, and in that data there were 1.4 million casualties, and out of those casualties there were 14,000 deaths over about 6 years. So I think it's important to remember that what we do with data analysis, modeling and prediction is can have a huge impact on people's lives. So okay, so I'll carry on. So I've done a quick project overview, which we've probably had this drilled into us now lots of times, and this is just basically how the project was structured by Rich and the processes that we went through and how it was broken down into the 6 pipelines, which is quite easy to understand. So in our data set, we had a great set of features, an enormous set of features actually, some of which were really cool. And because of that, well, not necessarily because of that, but we did also have a lot of missing data, as we can see from here, some more so than others. So we had a total of 861,000 missing values in our data set. So yes, we've got 1 million rows, but in those million rows, we've got a huge amount of features. And that was the total count of missing values. So what we did first, so basically what I've done is I've looked at all the notebooks of people that have helped, and I've basically implemented some of what they've done, some of my own stuff. But what I've done with this is I've took when it came to missing data, rather than try and use a mean or a median or a mode, I actually looked at the features and tried to see why there was missing data. And so the first thing I did was to look at any features that we didn't need, and obviously features a column. So out of all the features that I checked, we came to the conclusion that these columns weren't needed. So after removing those, we got our count down to 777,000 missing values. Then took it one stage further, and I looked at the features that were missing the most values, and it was the first and second row classes were the two big ones. And when I looked at those, there was a couple of things that sort of stuck out, and one of them is that the first and second row classes, what they basically meant was, for there to be a second row class recorded, there needed to be a second road as part of that accident. So, i.e. a car pulling out of one road into another, a car pulling off of a motorway, a car coming off of a roundabout, etc. So there was a lot of missing values in the second row class, and what that basically came down to was the fact that there wasn't a second road involved. So they weren't missing, they just needed a value to say that the second row wasn't involved. So I basically changed, we changed the values to a value that made sense to the EDA, that there wasn't second road involved. And there was a few others as well, and I'll just show you where I've got that, where I base my information on. And this is a part of the police form that they use to fill out when they have an accident, what they used to fill out. Sorry, it's not all there. It's quite a big form. And as we can see, we've got, so if we look at a road type, we've got 1, 2, 3, 6, 7, and 9. And what I found was in some of the feature sets, they'd have a not recorded or a unknown or things like that. And the fact that if it's in a lot of situations, especially in junction detail and junction control, you can only fill out junction detail if there's a junction control. So if there's no junction control, then the police officer would leave this blank, this part of the form here blank. And I think what happened was, in some of the features, when this was left blank, the person entering the data was entering not known or data not added or something, superfluous to use. So I basically converted all those to a no junction detail and did that across a few others, and that's how we managed to get the count down even further. We then dropped what was left of missing values. I then dropped those just using the just a drop in place. And after doing that, it meant that we actually removed less than 1% of the rows. I'm a little bit of a perfectionist, unfortunately, so I was driven by deleting as little data as possible, because I just worked on the assumption that the more data we've got, the more accurate the models and predictions would be. So what I then did, I looked at the collision severity spread, or what we did, look at the collision severity spread. So so slight, serious and fatal, we had a spread of 84, just over 84, 13 and 1.4%. And obviously the total number of counts of slight RTCs, serious RTCs and fatal RTCs. So what this basically did, it gave us a benchmark of where the average percentages were across the severities. So what the hope was going through the EDA, we'd find large increases in this fatal percentage against anything really. So, so yeah, so that's basically what we produce that for. So when it looked at road types, I'll just go through a couple of features. So when we look at road types, which is the class of road, like like in the UK, A roads are like a main road. Motorway is basically what it says, a multi-lane carriageway. And B roads and C roads are sort of second-class roads. And then we have unclassified. Now, what an unclassified road is a road coming out of a housing estate, or it could be a driveway, etc. So although it's unclassified, it's still a road and still counts. And that becomes important when we look at the second row classes. So what I did with all the none values, what we did, we converted those to no second road. So it just meant then that we could easily predict or easily check between accidents across one single road or two roads. And as it happened, the most accidents happen on A roads, and it kind of makes sense because there's more of those than any other roads in the country. And then pulling out of driveways or no second road were the second highest. So we then looked at hours of the day, and it highlighted the morning and late afternoon, and that was across all accounts really. And these are basically highlighting the 2 rush hour times of the day: going to work, dropping kids off at school, picking up kids from school. And interestingly, for both slight and serious, there was actually a drop off at night time, quite heavily at night time. Apart from fatal had a slower drop off during the night. So we also looked at day of the week, and again, Fridays for serious and slight accidents were seen to be the common day of an accident. But when it came to fatal, it was sort of Friday, Saturday, or sorry, it was Saturday and Sunday. We then decided to break down the time into seasons, and this is an overall accident percentage across the seasons. And interestingly enough, autumn, although it's not by much, autumn was the largest season for accidents in the UK of any of the years. And although it only shows 24% here, and spring 24%, interesting, winter and spring are the lowest. So you wouldn't have expected winter to be the lowest accidents, but it obviously is. Something else that we did, we wrote a function to pick out the dates where the bank holidays are in the UK. So in the UK, bank holiday is a holiday period during the year where we have a long weekend. And so what we did was we plotted the dates, and some of them were 3 days, some were 4 days, some were 6 days, depending on what holiday it was. However, the percentage is still at the average across the days. So Easter showed an 8% rise, May Day showed a 10% rise, spring 3%, summer holiday was a 34% rise, and interestingly enough, Christmas and New Year was a 19% reduction in accidents. So that was quite interesting fact, and a lot of that will be to do, especially the summer holiday, which is in August, end of the summer. It's the last holiday of the year, and it's probably the most people will be out on the roads with caravans, etc., going on holiday. So that may be a reason for that. You know, there is, when we look at this, it's quite obvious that if we had some contributing data to this, it would be awesome. Now in the UK, they do count the number of cars on roads on a regular basis, and it would be interesting to know if we could actually get hold of that data, because then we would know how many cars were actually traveling on the roads during those periods, and we could get an accurate insight as to why that rise is there. Is it because there's more cars, or is it because people are driving faster because they've got to get to their holiday, or is it because they're driving back from holiday and they're tired? So there could be things that we can't see in there that we might be able to pick out if we have some contributing data. Another interesting fact was pedestrian crossings, physical facilities. So basically what this means, it's a pedestrian crossing. I've got a picture here of it, which has a red traffic light to stop vehicles if somebody's pushed the button to cross the road. So there'll be a green light for the person to say, yep, it's okay to cross the road. On those particular facilities, there's 51 series RTCs per week. And out of those RTCs, sorry, that I've got 25, should be 51 there. Sorry. Out of those 51 series RTCs, 3 of them are fatal. So 3 people a week in the UK die crossing one of these crossings or a similar one, which to me just seems preposterous. I just can't understand how that could happen. So another thing we looked at was casualties, and looked at some averages, and with the percentages and the amounts we got, we worked out that on the UK roads, there's 1 death every 2 hours. Again, it's a bit of a reminder about how important this information is. So when it came to vehicles, as it did with casualties, there did appear to be some outliers. So obviously on this chart here, it shows that most amounts of vehicles was 1 and 2. So most accidents, it was either 1 or 2 vehicles. And then we have a whole range of other amounts going up to, I think it's about 36. Now, on investigation, there was, on the dates that some of these accidents happened, a record of an incident where 36 vehicles were in a collision, and most of them were on motorways, and they're what we call in the UK as pile-up. So, you know, 1 car stops, and then, you know, n number of cars behind them don't stop in time, and there's a big massive pile-up. So it's interesting to see that we didn't have to take those out. So another thing that we looked at was longitude and latitude. And when we looked at this, I thought it'd be a good idea to try and plot something here and see how that looks. So I used Folium to plot an interactive map. Now here it shows, I've managed to include some information as well, which gives you the area. Now I had to split it up into areas because to do the whole country was taking like 10 hours on my computer to populate and iterate through all the accidents to produce a map like this. So I broke it down into police force areas, and this is Thames Valley, which is basically where I used to live in the UK. And so on here we've got green for slight, blue for serious, and orange for fatal. So some of the takeaways, or the main takeaway, was that we couldn't distinguish between the severity of an accident enough to make a prediction. And I've just highlighted here that most of the graph, the distributions were very similar across fatal, serious, and slight. And because of that, we couldn't really make any pull out any insights to help model a predictive model, to help influence a predictive model to come out with some information that might be useful. Thank you very much.
That was spot on, Kevin. Very well presented, and I love the way you've used some of the code in there as well, just to show that what you've done. How did you find Folium? Working with Folium?
Yeah, really good. I'd used it before when I was doing some training, actually. And it's probably not the best one, but I found it quite easy to use once you've sort of grasped how it works and how you add the layers. It's actually a really, really good tool to use.
Yeah,
I'm
definitely.
just worried that it was quite slow. I'm not sure whether it's me doing something wrong with that, or whether that's just how it is, or whether it
Yeah,
performed
well,
better when it's actually on a
it's
server.
yeah, it's one of them. It's the more data you have, the slower it's going to be. Usually, if
Yeah,
you're going to do something like that, it's hosted on a some sort of cloud platform, and they've got plenty of computational power, so it runs
yeah,
quite quickly. But you know, a lot of people who work in data science haven't got monsters for laptops and computers, so it does take a bit of
no,
time. But yeah, really enjoyed that. Some great insights as well, and I think you know, you've captured most of what people shared and what people worked on individually throughout the group. So yeah, well done.
yeah,
Really enjoyed that. Okay then, and I think it's a good sort of you know a introduction to the next stage, which is the modelling. And the modelling is going to be handled by Michael. So Michael, you're more than welcome to share your screen and just talk us through the modelling phase, the experiments you ran, and you know, any difficulties you encountered.
Okay. Um, so, oop. So I'm going to talk about the road traffic collision modeling portion of this little experiment that we're doing here. For this, after all of our EDA and feature engineer, some light feature engineering, we decided to, we need to evaluate the model on our data set. I actually ran the evaluations on kind of two slightly different data sets. One of them was the accident only data set consisting of approximately 1 million entries. And the other one was the accident data set that had been combined with the vehicle data set on the accident identifier, which actually limited the data set down to about 600,000 entries. Then I tested these two data sets on several different models to see kind of which ones might respond the best. The one thing that kind of varied kind of wildly was the amount of time that it took for some of these various models to actually work. KNN and support vector classifier both took tremendous amounts of time to operate, and even if they were possibly more accurate, I don't know that from a computational standpoint they would make sense for a data set of this size. So speaking of what we were looking at, we were looking to predict our target variable, which was accident severity, being either whether the accident was a slight accident, a serious accident, or a fatal accident. After running all of the data through the various models, we're looking to predict how accurately, we're looking to see how accurately we can predict those various values. So we're looking for the positive predictive value. In just my initial run-throughs, the random forest classifier was kind of the most accurate. But one thing that I noticed when looking at this was, if you'll remember, Kevin so delightfully put that these numbers actually very closely match the data itself in terms of because there are so many slight accidents, the data is achieving a very high accuracy for predicting those accidents by essentially just always predicting slight accidents, which is an issue for us, which is called class imbalance. It's kind of the biggest problem that exists within this data set. We have a million plus samples. However, only 14,000 of them are our minority class, which is fatal, and that presents a problem for the machine learning models to kind of appropriately learn anything from the data, because there's just an overwhelming number of the majority class being slight accidents. However, there are a couple of techniques that we can try, which we did. Random undersampling, which essentially rebalances the classes, so it makes them all equal by just continuously it rebalances them by only sampling a small number of the majority class until you have the same number of all of your classes. So if we had 14,000 fatal accidents, it would randomly select 14,000 slight accidents to match that. In a very interesting turn of events, random undersampling actually causes us to we do gain accuracy in predicting fatal accidents, but we significantly lose accuracy in terms of our ability to predict slight accidents. So there is some improvement in terms of maybe determining fatal accidents, but not even then the ability to predict a fatal accident is not significantly greater than 50%, and so I don't know that it should be considered necessarily useful as a predictive means. Another way that you can deal with class imbalance is through synthetic minority oversampling, or SMOTE as it is sometimes called, which essentially balances the classes by randomly generating new minority entries, minority data points using a KNN model of the data. SMOTE did manage to slightly increase our predictive value, but when we later looked at that data against some additional data that was not that we had not used the synthetic oversampling on, it continued to lose its predictive case capability. This led us to thinking that maybe there were other insights that could be gained from changing the way that we are looking at the target variable. So the target variable, as it was originally defined, was either was slight, severe, and fatal accidents. We could reduce the complexity of the model essentially by having it only have to choose between either severe or fatal accidents by essentially excluding all of the slight accidents, or we could combine severe and fatal accidents into one category and compare them with versus the slight accidents. This binary classification actually did also initially appear to have a substantially increased accuracy, 95% accurate. However, similarly to the increased accuracy that we saw when using SMOTE, when we then again applied the predictive capabilities of that model against data that it had not seen, data a little bit further into the future from our extended data set, it was more accurate, about 85% accurate for predicting severe accidents, and about 30% accurate at predicting fatal accidents against one another. But that is a far cry from the 95%, and it still doesn't provide us with, fatal accidents are probably what we would most be targeting in this, and a 30% predictive capability for a model is not necessarily going to be an effective model. I think looking back at this, putting together the modeling for this, I do think that there was a lot of important information that was actually gleaned from the EDA that is very applicable in terms of what we eventually ended up, finding out by doing the modeling, which is that I don't think that this data models very well. I think that there is a large amount of randomness in what causes a road traffic collision to be severe or not. And I think that in some ways, this goes to show that governments have gotten particularly good, the local authorities have gotten particularly good at decreasing, glaring issues that would lead to fatal traffic accidents. And thus, the remaining the remaining road traffic collisions are just that, they're accidents. And so it's difficult for the model to pick out any sort of repeatable patterns because they may not be there to begin with. Another thing to consider that we didn't have, without discreetly having a client to work directly with, was what level of accuracy they were hoping to get with the model itself. As you can kind of see through a few of those slides before, some of these models were able to reach 50% or better accuracy for predicting fatality. That might for some clients be sufficient, and that would be something that might be reasonable to to present to a client at that point in time. And if it isn't, then it would also, and I think this was covered slightly earlier and maybe a little bit better, is that if you're talking to a client about the quality of the data, it might, possibly there could be improvements that could be made to this that would allow the model to be more predictive with better data or other things. Another thing that I did not try that might be a possible consideration for the future was I did not do any neural networks or deep learning networks. I don't know if they necessarily fit very well with this problem itself, but you never know necessarily how those things are going to respond. And so there might be some iteration of a neural network that might have some improved ability, though I think that I would likely side with the fact that I think that the data specifically for predicting high fatalities is sufficiently random enough that I don't know that there's any true pattern that could be gained. But yeah, that is where we ended up with the modeling.
Superb. Thanks very much. And yeah, you did. It's obvious that you've thrown pretty much every machine learning modeling technique to improve on the data we had there, and it seemed to, as you've said, not pick up any particular pattern. And I think you're very right in saying, over the course of time, local government associations and whatnot have really drilled down on their road network. So the accidents that are still happening could be just down to complete randomness, which cannot be predicted. It's a very difficult one. And in real life, as you say, we would go back to the client, figure out what they deem is acceptable, and see if we could improve on the data collection. One of the points I think is quite important in the accident data set as well, that some of it isn't actually from police reports, some of it is actually done on a self-service basis. So may have left out a lot of data that might have been important to model. It's them sort of considerations that we would have to take forward. But yeah, overall, great work, fantastic work. We've done as much as we can, and as I've said before, sometimes machine learning isn't the answer. Strong data analysis can is sometimes the only answer that you need, and it could, that's what drives the business decisions. There is a fine line between having a machine learning solution and a data analytics solution, but that's part of the process. That's what data science is. It's analytics, it's predictive modeling, and it's knowing when one will be better than the other. And I think in this particular project, we've demonstrated that at a very, at a good level. So thanks very much for that, Michael, and thanks for all your hard work. Always, Kevin, would you like to now share the solution? Do you want me to I'll restart the meeting because we've got 5 minutes left, and I don't want to let you get 5 minutes into it and then have to restart. So I'll restart the meeting now, and then the floor is yours. Just give me 1 second. Okay, Always, you can share your screen whenever you're ready. The floor is yours.
Okay. Can you guys see my screen?
Yeah.
Okay. So, hi everyone. I'm Wes, and I will be presenting the Streamlit dashboard that we have been working for the past couple of weeks. As mentioned earlier, the dataset that we are using for this dashboard is the same that we were using throughout the project, and it is from the Department of Transport, and it contains records of all the road traffic collisions or accidents that took place in England in a time span of 12 years from 2005 to 2017. While at the beginning of the project, one of the goals that we set for ourselves was to train a model, machine learning model that would be able to predict accident severity using the given data. What I mean by that is like if a traffic accident takes place under a given set of conditions, the model should be able to predict whether the accident was of slight, serious, or fatal severity. And as mentioned, it has already been mentioned by Michael and Kevin, despite the best efforts of our team, we were unable to do that. So while we were not able to develop a machine learning model, we were able to gather a lot of useful insights from the dataset, and that's the goal of deploying this dashboard. It is to cover and showcase some of the useful findings that we were able to extract from the data. So everything that you see here is mostly self-explanatory, but I will just quickly go over a few things to make sure everyone understands the user interface of the Streamlit dashboard. and get familiar with it, and everyone is able to make use of it for gathering insights once it's deployed and publicly available for everyone to use. So on the left side, you can see that we have main menu to navigate through the different pages of the web app. So right now we are on the accidents page, and under the main menu, you can see that you can see that we have three different filters. These two are the ear and the police force. The filters, these are normally called select boxes in the streamlets, and the severity status, it's called radio buttons. So the purpose of these three filters is that we can use them to filter data, and if you can see on the main screen, uh, these um, these four elements, uh, let me- uh, these four elements: the year, number of accidents, number of casualties, and severity status. These all respond to these three filters. So right now we are on year 2005, and the number of slight accidents in the year 2005 are 1729, and the number of casualties are 2323. So these are all responsive to these filters. So if we try to go to visualize another year, let's say 2008 or 2007. So these elements and the map will update accordingly. Uh, can you guys see the entire screen? It
Yeah, we can see the entire screen, but there's that box saying, please move this window away from the shared
yeah, but there
application.
is but
You
there
see
is
the map though?
no,
Yeah.
yeah, there is no window on my screen. So yeah, so yeah, so the map and these four elements are responsive to these filters, and the map shows the exact location of each of the accident, each of the these 1200 accidents, and if you click on any one of these accidents, it will, yeah, any one of these points on the map, it will show information about the accident, the collision, and uh, yeah, so these are the slight accidents from the year 2008, and to which the Wiltshire Police Department responded. So if we change it to serious, um, these numbers and the map will update accordingly. So now we can see that in the year 2008, there were 267 serious accidents and 429 casualties. And the same, if you click on any one of these, you will see the information to be of each accident. Similarly, if you want to change the police force, let's say Essex, or so now the map has updated and it shows the accidents that the Essex Police Department responded to, and these are the serious accidents. So you can switch between serious, light, and fatal. Let's see, we want to display only the fatal accidents. So these are the fatal accidents. Um, so one thing to notice here is that, as Michael has already discussed, that the imbalance between slight and the serious and fatal accident. So we can see that the number of fatal accidents are 69, and if we want to serious slight accidents. So the number of slight accidents are 3,678. So it just shows what Michael already mentioned, that we have a lot of a lot of data are of slight accidents, and we have very little data for the serious and fatal accident. So yeah, it's just showing the class imbalance. Another thing that has already been discussed by the EDA team is that if we go to the 2005 and let's just wait for it to update. So it's taking okay. So if we go to 2005, we can see that there are 4,595 accidents, and then if we move to 2017, you will notice that there is a significant decrease in the number of accidents. So yeah, it's something that has already been mentioned, that improvements may have been made to the traffic system or the roads that resulted in this decrease in the total accidents throughout the years. So yeah, that was all from the accidents page. And for the visualization page, I would like Kevin to take over and explain it, as he has already worked on the EDA, so he would explain it much better than me. Also, I want to thank Omdena for providing this learning opportunity, and also thanks to Rich and Salman for your continuous support throughout the project, and to all my team members. It was great working with you all. And yeah, so Kevin can take over, and he will explain the visualizations page.
Thanks very much. Always what you've put together there with Kevin is absolutely fantastic. Looks really good. Looks really good.
So I just thought I'd share my screen. Can everybody see that, can they?
It always, I think, still got a screen up. Yep, there we go. We can see your screen now.
So what I've done here very quickly, I just want to show on this accidents page. This accident here on the 13th of October 2016 at 8:25 in the morning was actually my nephew. So he had a car pulled on a motorcycle, car pulled out in front of him, and he lost the use of one of his arms forever, basically. So, which is being why it's classed as a serious accident. So I just thought I'd do that just to let people know how actually accurate this really is, and with something online that people can actually access, the public could actually go on here and look up accidents in real time for past accidents. So it's actually very powerful, I think, really. And if we look at the junction, it is really accurate, the actual position of the accident. If we look at the junction here, so here he was coming on his motorbike here towards the blue dot, car pulled out of this junction here to go straight across, and bang. So it just shows you how accurate and how important these things are. So basically what I did, I come along with and helped Oris on this. He did all the technical stuff, and I came along and did some of the design. So I basically changed it to a full width screen rather than the box screen. So basically what we do here was to add a little bit of code to stream it, to tell it to span the whole screen. It is responsive, so if we shrink it down, it does respond, which is quite good. So if you're on a phone, you should still be able to see it, and the menu pops out. And so I basically just added some. So with the visualizations, there is a lot more that we're going to do with this, and this is still a work in progress. At the moment, we've just got images here, but Oris and I are hoping to put in some real live plots, some of them which will be interactive, similar to the map on the accidents page. So this is basically a work in progress, but this is basically just a quick overview of what it will kind of look like. We also added an about page, which again is a work in progress. And this is just to explain to people when they come to the app what was actually happened, and what was done. Yeah, so really that's really all I've got to say about that really at this stage. I will be putting the code for this up onto the GitHub site and into the Slack channel.
Yep, that's fantastic. I've just messaged Oasis as well on Slack. If the limitations to like a free tier account on Streamlit, you know, were able to host this, it would do absolute wonders for your personal portfolio.
Yeah,
because it is a deployment, it's interactive,
yeah.
It has all the insights, and it has the sort of your thought processes behind deploying this and what insight you can derive from it. Very strong. It's, you know, in the industry, when you look, you know, when you're looking at data jobs, you know, whether you're a data analyst, a data scientist, or a, you know, strictly a machine learning engineer or whatnot, it's not necessarily your qualifications that set you apart. It's what you've actually done. It's the problems that you've solved that gains more. Like, I'm working, you know, I started in Capgemini. I've got no qualifications in computer science or anything like that. I am, you know, 100% self-taught. But what I was able to do is deliver examples of you know, things that I've worked on in other companies, things that I've worked on in my personal time and through Omdena as well. And that accounts for a lot. A lot of the sort of, you know, people who have experience in industry of data science between 10 and, you know, between about 10 to 15 years, a lot of them don't have specific qualifications in data science because it didn't exist then. It wasn't a term. They worked, you know, they started from a junior position as a, you know, in data analytics, and worked their way up without having any, you know, formal education in the subject. It's all learned on the job. So if we can use, you know, if you can use these your notebooks, the deployment in your favor, in your personal profile, you will go a long way, and it will really help bolster, you know, your reputation, your notoriety, not only to your network, but to your you know, a potential employer as well. So that is very important. And, you know, just being on Omdena and collaborating with other people shows you can work in a team, and you can, you know, you can even, you know, despite where that team is located, because in our group, we've got people from all around the world in, you know, 10 different time zones at least, and we've all come together, and you've built this, and it's fantastic. And, you know, even putting Omdena, you know, your contribution on your resume and whatnot is a fantastic idea. But to have a final product, which was the outcome of that, despite it not going the way we thought it was going to go, you know, a big problem has been solved. And, you know, who knows, who'll use this for insights. It's fantastic work. Great work, Oasis and Kevin. But yeah, as I say, let's see if we can get that on Streamlit. If it's not possible, I'll figure out a way to host it on, I've got loads of web space and things like that. I'll try, and if we can't get it on Streamlit, I'll see what I can do to host it on my website. And then you can just make a you know, a tiny URL link or something like that to it. Say, like, you know, this is a project that we worked on, and I have a live link there. I don't mind doing that whatsoever. Anything to help you out. Okay, fantastic. So we've reached the point where we can, you know, we can reflect on what we've learned, how you think the project went and whatnot. And what we have down, I know Francisca, she was going to share her insights and, you know, what she learned and whatnot, but she's unavailable at the moment. Something's come up, which is, you know, life gets in the way sometimes, and that's just the way things go. So the next person I had on the list for reflections was Joaria. Would you like to share your screen and talk about, your insights onto the project? You should be able to share your screen.
First of all, I will thank Chris for giving me opportunity for working in global team. Here we have performed analysis on UK government's road accidents data. I have chosen pipeline 1 for EDA for predicting RTC severity. Data in pipeline 1 was not labeled, so later on at model development stage, I also performed EDA on labeled data on accidents data file. So the EDA in presentation is combination of labeled and unlabeled data. I analyzed the data, its characteristics, then I performed EDA for on predicting RTC severity, performed model development and analyzed the data. By visualizing pipeline 1 data, it is already clean. Feature distribution represents that data is skewed. Accident severity, this feature is showing that 85.4% accidents are slight, 13.2% accidents are serious, and only 1.39% accidents are fatal. Days of week distribution represents that most of the accidents took place on Friday. By separating serious and accidents data, serious data from accidents and fatal data from accidents, the most serious accidents took place on Friday and most fatal accidents took place on Saturday. Peak hour of the day when maximum fatal accidents took place. Here graph is showing that on Friday most fatal accidents took place at 17 hours. This is again on fatal data. Accident distribution according to year is representing that most of the accidents took place in year 2005. Now, accident distribution in urban or rural area by speed limit. In urban area, most of the accidents took place at speed limit 30 and most of the accidents in rural areas took place at speed limit 30. Here we have counted, this graph is showing count of accident distribution in urban or rural area by speed limit. At speed 30, most of the accidents, mostly more than 55,000 accidents took place in urban area and more than 15,000 accidents took place in rural area at speed 60. Accident severity according to the road class, most of the accidents took place at road class A. Accident severity according to the road surface condition, most of the accidents took place at road class 1, that is on dry road. Serious accident distribution with respect to weather, most of the serious accidents took place when weather was fine, and similarly most of the fatal accidents also took place on fine weather. Casualties that took place due to the road surface condition, most of the accidents took place when roads were damp. Serious and fatal casualties took place on road surface conditions. Most of the fatal accidents serious accidents took place when at condition at class 5, and it is representing flood over 3 centimeter similarly meter, and most of the fatal accidents took place on snow or ice. Then number of casualties was showing many values, so I categorized number of casualties in casualty group size and here its distribution with respect to accident index. In model development, I merged accident and vehicle data on accident index, performed data cleaning and label and coded the data, created independent and dependent features, performed scaling through min-max scaler and applied machine learning algorithms. Random forest gave 86% accuracy, and confusion matrix for random forest represents that out of 95,318 accidents, 82,023 were correctly classified as fatal, 2 as correctly classified as serious accidents, and it 13,293 were wrongly classified. Here rock curve is showing AUC value 0.83 for class 2.70 and for class 3.72. ADA boost is also giving accuracy of 86% accuracy. Confusion matrix of ADA boost is representing that out of 95,318 cases, 81,837 were correctly classified as fatal, 183 correctly classified as serious, and 16 correctly classified as slight accidents. So total 92,036 were correctly classified and 3,282 were wrongly classified. Similarly, ADA different values for AUC for different classes, true positive and true false positive rate. XT boost is also giving 86% accuracy. Confusion matrix for XT boost is correctly classifying 82,076 as fatal, 105 serious accidents, and 4 correctly classifying as slight. Rock curve 0.84 value for class 1, giving 0.71 value for class 2 and 0.73 value for class 3. Here, by comparing most, all 3 algorithms are giving accuracy around 86%. Takeaway from the course is that we have to, I want to further analyze and explore by experimenting that either with, perhaps I can find out some features or by combination of different features, some thing that can help to avoid collisions. So in this way we help the community for avoiding accidents, and this would be our contribution towards society. And again, thanks the Salman again, I would thank Salman for guiding and helping, and other group members whose work encouraged me to work.
Headsets or something like that. Try and taking it out and replugging it in, and hopefully it will it'll sort itself out. Okay, Lavanya, do you want to go ahead and share?
Rich, hi everyone. Like, I don't have the presentations where I can talk. It is a presentation is same like what Shravan has presented on the EDA vehicle data analysis. I'll just talk about my experience on the Omdena, like how I started my journey. Yeah, that'll be fine.
Yep, absolutely. Go ahead.
Yeah, thank you, Rich. As I say, like I'm a beginner in the data science, so when I joined the Omdan, like I felt like what I'll be learning. The first week I was very scared, like what I'll do because I'm very beginner in this field. But the process, like the went on the meeting, the gathering, and also the on the discussions in the Slack and all, I felt very comfortable with the team, and especially the really like he helped me a lot in the standing of the stage, like the data extractions and all. I learned a lot in the Google Colab, like on the Paraquet, how to extract the files and all. Also, I worked on. I've joined Salman's meeting also on working on the missing ID, missing values, how to impute the missing values in the different ways. Because till now I know only mean, median, and the mode, but I didn't know like there was so much vast, like so much deep analysis we can do in the missing imputations, which actually affects our analysis in the further process. So I learned those things and machine learning algorithms. These things, I felt it was very good. Like I love to work with the team on done projects on in the further future also. Yeah, this is what my experience in the working on the projects.
Cool. It's good to hear, and it's good to hear that you've learned a lot. And what I'd like to say as well, Salman will be, he was ill over the sort of final part of the project, so couldn't do as much code alongs, but he's going to continue doing that. If you've got him on LinkedIn, I think he announced he's going to be doing it every Monday and Wednesday, I think it was, and he'll be doing it through our YouTube
Monday,
channel.
Wednesday and Friday.
Yeah. It'd be a good idea to basically carry on listening to Salman is a very talented individual. He's been doing sort of machine learning since about 2008, I believe, and he has a mathematics background as well. So he's able to, he'll be able to walk you through, a lot of different techniques and whatnot through the entire data science life cycle as well. So this is not just for you, but for everyone. It will be a good idea to to follow the channel, keep in touch with Salman, and attend as many of his sessions as possible. Once I know where my what my roles and responsibilities are within my new job, I'll be also doing code alongs as well. If time permitting, will be doing them live. If not, I'll just record them and upload them to the YouTube channel as well. Mostly, I was thinking, Salman's doing a lot of the data pre-processing and things like that. I'll probably do something more around model deployment and model sort of maintenance in terms of monitoring data drift and things like that. So the sort of MLOps side of it, I'll probably do just so we don't step on each other's toes in terms of content. So yeah, but thanks very much for being on the project, Lavanya. Your insights have been very valuable, and it's good to see that you've come a long way and got more confidence in dealing with the data, and you know, you haven't been intimidated by the size of the data and you know what's gone on, you know, in various different parts of the project. So that's fantastic, and you know, I'm really glad that you did enjoy it. Shravan, you have got your hand raised.
Yeah, Rich. Well, I wanted to give some like present something that I've learned so far. Um, am I audible at the moment?
Sorry, say that again. My dogs were barking.
Am I audible, Rich?
Yeah, you're audible. Yep.
Yeah. Okay. So I really enjoyed the whole 5 weeks of the Omdena project, and I found this opportunity really great because since I had recently graduated as a computer engineer, and I had dreamed to proceed in my career into the data science field. So this project helped me get inspirations and move towards the path of the data science. And I'm very much thankful to Rich and Salman and every team member. Because of them, this project has been successful. And some of my key takeaways from this project was like, I found that data science is really very iterative, right? And we do a lot of, I have found that we just iterate over our abstractions that we pose on some problems. So I found that we have some abstract to start with and then go deeper. And I found that we should get with the base model by getting like minimal features and try to get a best model and try to improvise it. I learned about that. And yeah, cheers to EDA, because I found that EDA itself presents a lot of insight for the business decision. And I really enjoyed the EDA phase itself. And yeah, I found that domain knowledge is must, because if you don't have a person working in a team who have knowledge about what we are working for, like we need to know about the problem first understand the problem and then think for the coding first. So I learned about it. So there are no data science unicorns. So as while working with a team, and I had experience with someone doing great for their feature engineering, someone doing great for their EDA. And yeah, and I also learned about a lot of automation tools that we could automate, automate to understand, to gather like features, and automate to register the models, and like validating it. And also the most important thing that I've learned is that get the assumptions right before applying any machine learning algorithms, right? So every algorithms have their underlying assumptions. So before applying any fitting any data to it, algorithm for building a model, you just get the assumptions right. Every algorithms have their own assumptions. You need to know about them, how they work, and then go for it. That's pretty much of it. Thank you all.
No, that's really some, you know, great takeaways, and every one of them is absolutely true. Data science is very iterative. It's, you know, if you can have a certain direction, a certain business question, and you could attempt to work on that, and you know, when you get, you know, further down the process, something could change. You could you know, reveal something that was previously unknown, which makes you go back to your data pre-processing and start that part again. That's what it is. It's a constant iterative process. And you know, just because as well, you know, when you get to the modeling part and the deployments part, when you deploy a model, you have to maintain it. You have to, you know, make sure it's still producing accurate results in a year's time, in 2 years' time. And what you have to take into account is the fact that data will change over time. And so, you know, you may not have to go all the way back to the beginning, but you know, these are the sort of considerations that you have to take. I completely agree with domain knowledge. Most of the time, you know, anyone can learn technical ability in terms of programming, mathematics, and you know, model building. They can be learned over time. That's not a problem. The most difficult, a lot of the time, is the domain knowledge, especially if you work for a company which is very project based, which has a number of different, you know, IT consultant firm may have a number of different clients that are in completely different industries. And if you're working as a data scientist there, you'll be put on these different projects, and you know, you may be put on a sort of bioinformatics project, and you might not know much about biology. You might remember, you know, your high school teachings, but you'll have to learn that, as well as, you know, trying to figure out what would be the best approach to handle their type of data. So, you know, it's data science, machine learning, you know, data analytics, anything in the data field. It's a constantly evolving and constantly, you know, it's a lifetime of learning. And if you are not able, if you don't appreciate to learn, if you don't like to learn, you're not going to make it in data science. So you have to have that sort of mindset where you are a sponge for new information. You're a sponge for trying things that, you know, have worked in the past, but will not work on another client's data and whatnot. It's a complete, you can't master it all. It's always, you're always going to be on a learning curve. And personally, that's what I like about it. I like the knowledge that is gained, and I know until the day I die, I will be learning more and more every single day. And I like that. Some people don't like it, and they won't ultimately cut it in a data science role, because that's what data science is. It's a progression of your own knowledge. And as more research goes on into machine learning, AI and whatnot, the more tools are going to be passed into industry that we as data scientists have to use and have to learn. So it is a very exciting field, but I tell you, sometimes you know, your brain is completely fried, but you know, that's a good thing. A very important sort of lesson is, you know, I'm one of those people who can hyper focus, and I could sit at the laptop for hours upon hours, and that's not healthy. You need to take a break, especially in this sort of in this industry. So yeah, Lavanya, if you've got your hand raised, and we'll go back to Jawaria after this, but go ahead, Lavanya.
Yeah. Thank you, Rich. Like, I just want to thank everyone on the team, like, who helped me. Actually, I can see, like, my background, the domain is human resource. I was a manager. So I just thought, like, I'll shift my field. So I thought, like, data science and all. When I entered the data science, this thing, I thought, like, because it was a different domain, I will not be able to cope up with this. But seriously, like, I've learned a lot, and I worked on, like, working on these projects. I learned so many things with the coding, and the simple coding I used to know. But when I entered this project, I was learning with the different techniques and all, because I used to write a lengthy code. But when I on this project, I was I knew, like, it was a different, like, one single line only we can work on that.
Can anyone hear me?
Hello.
Yeah, we can hear you now, Jawaria. Well, I'll pass it over to you once Lavanya's finished.
Yeah, this is like which this project helped me a lot in learning those things on the coding part, and as well as on the thinking side, like, which, because when I interacted in the Slack, and also I'll be, okay, this way also we can do it, this way also we can do it. So this is all like a team effort, I can say, like, because all the team members, like, I learned a lot from everyone.
Good.
This is what I just want to say that. Thank you, everyone.
That's good. That's good to hear. And a very, you know, I appreciate the feedback. Jawaria, do you want to share your screen? And so what we'll do, we'll leave it there. I just want to say thank you, everyone, for contributing. It's been a pleasure working with everyone over the past couple of weeks. Remember to add everyone that you've worked with, or add everyone that you haven't worked with, have everyone in the group onto LinkedIn. Please endorse people for their skills. and please leave recommendations as well. I'd appreciate it if you could also leave recommendations for me, and I will, of course, leave them for you as well. As I say, it's been a pleasure. It's been good to see everyone grow, in terms of, data science, coding skills, methodology skills, and whatnot. It's been really good to see everyone contributing and producing something that you should be really proud of. But yeah, Jawaria, record your meeting, please, and I will add it to this recording. I still have to I'm going to upload last Saturday's recording as well. I've just had a bit of technical issues with my personal computer and the record. I don't know what the hell was wrong with the computer, but I think I've fixed it now. But as I say, it's been a pleasure working with you all, and the Slack channel, it will be kept open. So please feel free to catch up and whatnot in the future in the Slack channel. Upload all your notebooks to the GitHub, and please upload them to the data set that Salman's uploaded on Kaggle as well, because it'd also get you some reputation there as well. So again, thank you everyone. It's been a wonderful presentation. It's been a wonderful experience, and it's been good to get to know everyone. And yeah, I'm sure we'll be working together again soon. And yeah, I look forward to it. I'll see you around, everyone.